So Daniel, we are happy that you are here. This is your stage.
Thank you for the introduction. And yes, I will start right away. One fault attack that you might know is the rowhammer attack. And if you don't know it from research, you might know it from the television.
The hacker used a DRAM rowhammer exploit to gain kernel privileges.
Hey, Chuck. Yeah, I've got something for you.
So this DRAM rowhammer exploit to gain kernel privileges works like shown in this example, as we have shown in 2015, also from JavaScript. Here we hammered in JavaScript. You can see the lower part of the histogram, and then you can see that bit flips were found at different offsets in this array. So this is, of course, very powerful, but we want to know how this works. So this was 2015. We presented it at CCC then also in 2015. That's almost 5 years ago. So how does this work? We take the DRAM module first, look at the DRAM module, and the DRAM module has multiple channels, maybe if it's installed in a computer. Each module has multiple sides, and we call them ranks, so the rank 0 and rank 1. And if we take a look at a chip in more detail, then each chip is again comprised of many, many banks for more parallelism. And these banks each have a lot of rows. And these rows, to access them, we also have a row buffer here. To access them, data is copied into this row buffer, but more on that in a second. These rows are now composed, they store the actual data. They're composed of these capacitors and transistors. And each of these rows is exactly 8 kilobytes in size. On a DDR3 module, you will find that we have 8 banks. On a DDR4 module, it would be 16 banks. So there's more parallelism. Now, as I said, reading from a DRAM bank means copying this from the bank, from the row, into the row buffer of this bank. There are two effects now that we want to understand. The first is that capacitors over time discharge, so we have to recharge them frequently. We have to do that in our DRAM modules within 64 milliseconds. Data is only guaranteed to stay in the DRAM if you refresh within 64 milliseconds. If you wait longer, then the data might be corrupted. There's a second effect, and this is the so-called rowhammer effect. And the rowhammer effect will cause leakage from capacitors if you access capacitors that are in proximity. And this effect, if you would exploit that, for instance, like here, you copy a row into the row buffer, then you access a different one, and then again and again in the middle row after some time, you will have bit flips. Now, how widespread is this issue? If we take a look at DDR3 and DDR4, for instance, in DDR3, we had a study in 2014, which is probably the best prevalence study here, which said 85% are affected. In 2015, we had a study by Seaborn and Dulian that found 52% were affected, but they had a very constrained hammering function, so they probably didn't catch all of the vulnerable laptops. So this is probably closer to the truth. DDR4 was first believed to be safe and claimed to be safe. The DRAM vendors went out and said, "Oh, we have mitigations. Everything is safe here." But we showed bit flips on DDR4 as soon as we were able to get DDR4 modules, and that was in 2016. Later on in 2016, also Mark Lantain showed that 67% were affected. And there was also a recent study, I think from this year or last year, that also showed that it's approximately in this order of magnitude. So how does this look? This is the figure from the 2014 paper by Kim et al. And you can clearly see two things here. The older modules didn't have any bit flips. This only started at some point. One suspicion is that it has to do with the manufacturing size. So things get smaller and smaller and smaller. And that's why you now see bit flips. And you didn't see that earlier because the sizes were still large enough. You also see this effect that older modules have more bit flips than newer modules. And there are two explanations that try to explain this effect. One is that the manufacturing process gets better and better over time. The other explanation is that there are also some aging effects in DRAM, and these aging effects cause more bit flips on older modules that have already been used more. But anyways, you can plainly say bit flips, like with 85% affected, bit flips everywhere. So the question is, what can we flip? And in this case, we will take a look at opcodes. We want to flip opcodes. Previous work has, for instance, looked at flipping bits in cryptographic keys, in page table entries to gain root privileges. And we also looked at flipping bits in instructions in a binary. So in this case, we looked at the pseudo binary, and in the pseudo binary, there's a conditional jump, and this conditional jump uses the jump equal instruction. And the jump equal instruction will branch to a function if the password was correct, if it was equal. And if we flip a bit in there, maybe this bit, this becomes the halt instruction, not very good. This would crash our program. Let's continue. Okay, this at least doesn't crash our program, but maybe it's not so helpful. Maybe. Oh, this is great. Jump equal to jump not equal with a single bit flip. So that means if we flip a single bit with the rowhammer, we exactly invert the logic of pseudo. And now everyone who enters the correct password cannot log in anymore, or cannot gain super user privileges anymore. But anyone who enters the wrong password will get the pseudo privileges. And the question then is, if you are able to flip bits like that, what can you do against that? And there's one security technique that many people find very interesting, and I also find that very interesting. It's the SGX technique. Intel proposed SGX as a way to make it possible to run code on a system that cannot be manipulated, even if the operating system is compromised. So how does this work? We have an application, and the application now consists of an untrusted part, and this untrusted part can create an enclave, and this enclave then will run trusted code that is signed and that is secured with the root of trust lying at Intel. And Intel's security guarantees claim that as long as it's signed, everything should be fine, and no one will be able to tamper with the execution, read the data. Maybe if it's encrypted data, no one should be able to read it. No one should be able to influence the control flow, etc. So it should be secure and also to some extent secret in there. Now the enclave is created, and if we want to call a function of the enclave, this works pretty much the same as system calls in operating systems. So we call a trusted function, it goes through a defined call gate that the enclave defines, and from there it hands over control to a trusted function. And this trusted function is then executed. This is the trusted part. So this builds on the same security model as operating systems also build. The trusted part is controlled by the developer who can be trusted and is signed, and therefore this is a meaningful isolation. As soon as this function is done, it will return and will go back to the user space, to the untrusted part of the user space, and there we continue the regular execution. The interesting part here is that not only the untrusted part cannot access the trusted part, but also the operating system cannot access it. And not even with a cold boot attack would I be able to get the data from here, because this data is also encrypted in memory in this EPC region here. This EPC region is encrypted. And of course, they also took care to not run into the very stupid mistakes like providing encryption, but no integrity and no freshness. They provide that. So this is also secure against replay attacks. So what happens then if this is integrity protected? What happens if there's a bit flip in the EPC? Good question, good question. The integrity check will fail. So it will lock up the memory controller, and not a single further memory access can happen. This halts the system immediately. No data is written back to the disk. No data from the cache is written back to DRAM. Nothing works anymore. This halts the system immediately. Yeah, sounds unsafe. it is unsafe. Think about what happens if this is used by an attacker. So if a malicious enclave intentionally induces a bit flip in this region, the entire machine halts, including co-located tenants in the cloud. And this is a very cheap denial of service attack in the cloud. We published that in 2018. This was concurrent work with a paper by Young et al. In 2017. We also went one step further and combined this with basically not hammering the SGX EPC memory, but hammering the normal world memory. And what happens? So SGX protects software from malicious environments. We just said that. And this includes also static and dynamic monitoring, static and dynamic analysis, for instance, with performance counters. So if you hammer from SGX, then countermeasures that rely on detection cannot work. So you basically use the security technique to hide your exploit. So this is, of course, a very nice way to build an exploit. How does this work? We can see a demo here, and you can see on the left side, this is a regular installation of Linux inside a virtual machine. We are not the sudo, but sudo version is fine. We are not the sudo. You can see that in a second. Now we run the exploit. We inject the bit flip, and now we are able to later on use sudo. We now skip the password check. We are root. And very nice, if we now evict the data from the cache, from the page cache, it's restored and all traces are gone. So we even cleaned up all the traces. No one knows that we just exploited sudo. Well, you could say at least it's a local attack, right? At least it's a local attack. But I want to compare the performance numbers here just for a second. We need 43,000 hammering attempts for a bit flip. 43,000 accesses to DRAM within 64 milliseconds. That's 700,000 accesses per second. Network packets, we looked that up in the Linux kernel, access the same memory location up to 6 times. That would mean that we would have to send something like 120 memory packets to a system, 120 packets, 1,000 packets per second. And this would lead to something like 700,000 memory accesses per second. Network packets are at least 64 bytes in size. So if we multiply that up, this would lead to 57 megabits per second. Doesn't sound very unrealistic to send 57 megabits of data to a system. And we also showed that this is doable on modern systems. To induce a bit flip, though, we required 600 megabits on the systems that we had. Now, this is Rowhammer, and the part about flipping bits in SGX is a bit sad because we wanted to make sure that we can attack anything with that. So SGX more or less mitigates the Rowhammer attack or fault attacks on SGX enclaves. But what about other attacks? For instance, on ARM, we have seen Clockscrew a few years ago, which attacked ARM Trust Zone, which is also a TEE. How did they do that? They manipulated the frequency of the processor such that voltage and frequency don't fit together anymore, and the system was not computing correct results anymore. So how can we do that on Intel? Actually, I used that a lot because I had a laptop in 2008, 2009, around this time, that was very unstable unless you undervolted it, because it was overheating all the time and then turning off because of overheating. So what I used there was an undervolting tool. And there's also a PhD thesis that describes these undervolting MSRs in more detail. Here's this MSR that we use for undervolting, MSR 150. And there we can change the voltage offsets, we can change the voltage planes and change it to a lower level so that we consume less power, creating less heat. But at the same time, this should have a similar effect as overclocking. So let's take a look at what we can do here. We have this simple code with a correct and a correct multiplication and another multiplication. And what we will do is we will check whether the result from this multiplication will be the correct result. And we compute this again and again. And this is all computing just the same. Will this create bit flips? Let's have a look. So here we run exactly this example. We open the MSR, we set the undervolting value. Now we are undervolting, minus 253, 55, 56, 57. And there we have a bit flip. And now we check what the result was, the XOR result. So we can see that one bit was flipped in this character. And we can try that again with other undervoltage levels. So you can see how far we undervolt, and you can see there's more bit flips, similar bit flips. And another bit flip. And another bit flip. So we can have a lot of different bit flips here. And we actually evaluated this across different frequencies and voltages. And you can see that the base voltage that the processor would choose is a significant step higher than the voltage that we needed for the first flip. But you can see very well that it's not that far off. And if I would undervolt a bit to make my system more usable, then I would quickly get into this range where bit flips can occur. The other part is that changing the voltage only needs root privileges. So if we have root privileges, then we can change the voltage. Here's a thesis from Twitter. Someone suggested, given a cool name, researchers will be able to find a new vulnerability to match it in a finite period of time. Cool name logo combination requirements have no measurable effect on the aforementioned period. Let me just move to the other window here. Okay, so let's do that. Let's come up with a cool name logo combination. A volt hammer, for instance. Volt hammer like row hammer, but volt like maybe like volt undervolting. Maybe that's an idea. So what about SGX here? Can we induce bit flips in SGX? And again, we will check how that works. And you can see that we have bit flips here in the SGX enclave. So we now can introduce bit flips in SGX and can attack SGX enclaves with that. Great. So maybe we should call it like that, SGX and then screw, like clock screw, SGX screw. Yeah, maybe that's a good name. Or maybe we should first take a look at what else we can attack. Maybe not just multiplications. Multiplications are boring, right? So let's attack something else. Let's attack RSA. RSA, public key crypto. You can encrypt or sign messages. You can decrypt, sign, or encrypt, verify messages. And you can then send messages over an untrusted channel with that. So for the basics, you need some prime numbers there. Then you compute a modulus. Then you can generate a signature by computing the hash of the message times to the power of d. And what you do next is you want to basically make this operation cheaper, so you can instead perform these two operations so that everything runs a bit cheaper, a bit less of exponentiation. This is, of course, a lot of mathematics, and now to compute a signature, you also have to change this and use these two parts. This is a Chinese remainder theorem. And of course, this is a lot of mathematics. There's a lot of mathematics behind that. And it would take a long time to understand how this works exactly. But I want to focus on exactly the signature part here. Let's assume we can fault a signature. Then we have basically one signature that is correct and one signature that is wrong. So we'll have two different signatures. And this part here will not be the same. So it will be something and something else. We don't exactly care about what it is and where it comes from. It's just one has one value, the other has another value. What do we do with that then? We multiply it with Q plus S2. S2 is public, Q is secret. But we now have basically, if we subtract S from S prime, we have something times Q, which is great because now we can just go and compute the GCD of this difference of the signatures, and N is also public, so we can get Q. Very nice. And then of course, if we have Q, we can also get P immediately by computing the GCD of Q and N. So let's attack RSA. In this case, we will again attack a library, or we will actually, for the first time in this talk, attack a library that is used in the real world. This is the Intel library, IPPS, and we use the RSA decrypt function there, and we will trigger a fault. So let's take a look at how this is used. Then we have some delay function also to get to the undervolting part to get this aligned to the right offset. And then we undervolt, and at some voltage we have an RSA error. This is nice because now we have a faulty signature and a correct signature, and we can just feed this into a Lenstra attack and check what the output is. We have null x e c f a something. And let's check. Oh yeah, this is exactly the key that we have implemented in our enclave. Perfect. So we just got an enclave key, an RSA key out of an enclave. We could call it Mufasa. This would be a very nice attack name. Mufasa, my undervolting fault attack on RSA. Very nice. What else can we break? We can also break other crypto. We can break symmetric crypto, for instance. There's AES. AES allows you to encrypt messages over a untrusted channel, or over if you want to store data on untrusted storage. And it is symmetric. That means that both parties need the key beforehand if there are two parties. It has a 4x4 byte state. It has 10 rounds, S-box, shift rows, mixed columns, add round key in basically all of these rounds, plus minus a bit. And if we take a look at the last few rounds, you will see that a bit flip here will propagate in a way through the last rounds. This is the 8th round. And the bit flip will propagate in a way through these last 2 rounds that it can be computed back how this propagation is. We will know exactly which bytes here are influenced with some probability. Now we want to attack, of course, an AES implementation that is used in practice. And in this case, we will attack AES-NI. And AES-NI uses these instructions to implement the encryption with multiple rounds. So we do that. We just use the AES-128 encryption function here, and we compare whether the two results of the encryptions of these two encryptions are the same. So we do that, we undervolt, we run this, and here you can see that there was a fault in some round, but not the right round. Not the right round. Oh, here was something. This is already better. In round number 8. And now we have faulty pairs of ciphertexts. And we will run a differential fault attack here, and we find that only one pair remains, one key remains. And you can see that this is exactly the key that we entered in this program. So the differential fault attack here worked successfully. So we could call it crypto vault screw hammer, maybe, because it's crypto, it's vault like SGX, screw like clock screw, hammer like row hammer, all of that combined. I want to have this tool. If someone finds it on eBay, please tell me. I would like to buy it. I don't know what it's useful for, but it looks like a crypto vault screw hammer. But you can also attack other things. For instance, you could corrupt memory. Let's corrupt memory. You might see it already, but here's a multiplication in there. Pointer arithmetics. Pointer arithmetics, you have multiplications with size of the base type of the array. And of course, we can fault multiplications, and we will do that. We undervolt again, and you can see that we, in this enclave, we will write to a memory location, to this memory location here, and we should not write out of bounds. We should not write beyond this one. And let's see what happens. We try this a few times, and at some point we get a fault. Oh, and the address changed. This is now pointing somewhere completely different. So if we write there, so we are trying to write there, continuing to write there, and then suddenly the address is faulted, and we write somewhere outside into the normal world memory. And there, of course, the operating system, which can be malicious, can map a page and just read what the enclave wrote there. So now we again got an enclave secret, and this time through memory, faulting memory addresses. So we should come up with a better name. It should be related to undervaulting. It is getting secrets from protected TE vaults, undervaulting vault. We steal, we corrupt, we plunder. That's plunder vault. That's the second attack that I've shown today besides row hammer. And those are both attacks that we can use to fault hardware from software. And with that, I'm already at the end of my talk, and I would be available for questions.